example of conventional GNSS ranging positioning in deep urban environment. So we can see there is a 30-meter horizontal average accuracy for this particular example. So our research is about reducing or improving this accuracy, basically reducing this number down to sub 5 meters. And for this, we try to explore 3D mapping. The problem with GNSS in the deep urban environment is the existence of buildings that do block signals. Besides blocking signals, those signals can also be reflected. And if the user is receiving a signal by a reflected path, the deduced positioning is erroneous. So the aim is, by having 3D model, we know where the buildings are and we know the terrain height. So effectively what we are doing, after we've taken the opportunity of existence of a lot of measurements from multi-constellations and development of many algorithms over a decade of research, we are now trying to exploit the existence of 3D mapping, starting from simple, what we call block maps, like OpenStreetMap or from national mapping agencies. So we won't be starting from even complicated 3D models. So 3D model GNSS can be performed in 3 ways: height-aided, mapping-aided region, and shadow matching. For height-aiding, we exploit the terrain height, and from this we construct a virtual range to a satellite which is located at the center of Earth. In an open environment, we get improvement on the vertical positioning, but in an urban environment where we have poor geometry of satellites, we improve this geometry by adding the virtual range, and hence we improve both vertical and horizontal positioning. Mapping-aided ranging can be performed using different approaches, but the generic principle is as follows. Instead of starting with the actual GNSS positioning or location, we construct a grid around the position provided by the GNSS receiver. That grid needs to be large enough that we have a likelihood that our actual position exists within. And from that grid, we use our 3D building, our 3D models, and we calculate which satellite are line of sight, which satellite are non-line of sight, and we use predicted and measured pseudo ranges to basically derive information to score each particular grid point. So we provide ponderation for each grid point, and the point that has got the highest score is the likely point to be correspondent to the closest point to the actual position. The third approach is shadow matching. It has been proposed to tackle the problem of poor accuracy across the street, because across street direction we have less visibility of satellites compared to the along street direction. And the principle is as follows. If we know our 3D model, and if we know the elevation of one of the satellites of interest, then if we can receive a direct signal from this satellite, we are likely to be in the green area on the left plot. If we don't receive direct signal, we are in the red area. If we repeat this process for second and third satellite, we are effectively reducing the error position. So we are improving our positioning. So effectively what we are doing is we are exploiting non-line of sight and untracked satellite and making them contribute to our position, which is the opposite what GNSS does. The two last methods, the 3DMA, GNSS ranging, and shadow matching, both incorporate a pre-processing step. And this involves the use of the actual 3D city model and the prediction of line of sight and non-line of sight. Most research groups use either ray tracing or specialized hardware to basically derive the line of sight and the non-line of sight prediction and feed them into GNSS positioning algorithm. At UCN, we found a compromise between processing load and needed hardware to perform this task. So we translate our 3D model into what we call built-in boundaries, and we feed those built-in boundaries into our algorithm to calculate the position. So the first process is as follows. We start with the building footprints. This is an example from the OS master map data. And we use building height information. In our case, we use the relative height to extrude the data. And from that extrusion, we calculate our building boundaries. The way we do it is that from a user vantage point, in this case, it's one point of the created grid, we calculate the elevation to the building from which beyond we can see satellite and below we can't see satellite. And we do this for every azimuth. And then we'll end up with file where we've got azimuth angles and elevation angles for each point of our grid. So we performed a couple of tests using consumer-grade receivers and using smartphone-like receivers. And we demonstrated the efficiency of our 3D mapping aided GNSS. The performance achieved using consumer-grade was factor of 7. So basically reducing the error from 28 meters down to 4 meters. And using the smartphone-like receiver, a factor of 4. The reason there are differences between those, the result for those two receivers is that the actual antenna used for both receivers, the antenna for GPS receiver or GNSS receiver is well adapted to receive the direct signal and have some mitigation towards reflected signal, but the antenna on the smartphone-like receiver is linearly polarized and it absorbs both direct and reflected signals. So we need definitely more accurate terrain height information and building modeling because our approach is all based on the actual 3D model. So we started looking at different errors that we get, and specifically errors in the building models. We classify them into errors that give us small positioning errors, and into building modeling errors that give us large positioning errors. For example, building position errors, omission of building details, for example, roofs, it depends on the city model's level of details, and this, we estimate that they will provide us sub-meter positioning error. The most difficult building model errors are the ones occurring from new buildings, which are missing from the database, demolished buildings, or coming from very distant buildings, for example, in this illustration, that could affect GNSS reception, where they either block the signals or reflect very strong signals towards the user. So we looked at the way we select the height of the building from the 3D model. We have different 3 options, for example, in the OS master map, either select minimum height, the average height, and maximum height. Because building boundaries is one of the important data we use in our algorithm, we evaluated what are the building boundaries extracted for one point of the grid. And there is definitely difference, even almost up to 10 degrees difference, whether we select the minimum height, the average height, and the maximum height. And this is for the same database. We've also looked and compared results from different databases, from Open Survey Master Map, from OpenStreetMap, and from VectorMap. And also we can notice that the result we get and the extrusion we get are different. And the densities as well are different, and there are missing buildings between those different databases. We perform some similar analysis, but now cross databases, and we can see that there is a large error dependent on the choice of building height that we go for. So our future work is perform practical tests to assess the impact of elevation variation in our algorithm. We also would like to look at the reflectivity parameter of the buildings, because this is an important parameter that will let us know whether we need to consider the reflected path or not, whether the signal that will be received by the user will be weak enough or strong enough. And the last part is that we will look at the impact of higher level of details on the positioning performance. Thank you for your attention.